All right. Our next speaker for the session is Boris Ragula, and he's going to talk about entanglement harvesting from the gravitational field. Boris is just a recent graduate, graduates, if you want, from the University of Waterloo. Boris, the floor is yours.
Awesome. Thanks, Edu. As just stated, I'll be talking about entanglement harvesting from the gravitational field. This is some ongoing work I have in collaboration with Rick Hirsch and Eduardo Martinez. So really quickly, just the outline of this talk. I'll give a brief introduction, and then we'll talk about quantum fluctuations on a Minkowski background. We'll talk about the coupling of quantum matter with gravity. We'll show some results that we have right now for entanglement harvesting from gravity, and then do a couple of quick conclusions. So for about 100 years now, as we've seen in a couple previous talks, we've had a theory of general relativity in quantum fields. However, we've yet to provide a theory of quantum gravity, and there are many theories that have arisen in an attempt to describe the quantum nature of gravity, but none have been successful in providing realizable results. However, quantum field theory is expected to describe gravity in the weak field limit through linearized quantum gravity. And I will be presenting our research on a method we believe may help us start to understand this quantum behavior of gravity. And to do so, we will be using unroot detectors. So as we know, UDW detector models have been used to study a number of phenomena in quantum field theory. And as mentioned in Rob's talk, UDW models can probe the Unruh effect. They can probe space-time topologies and geometries, describe communication protocols in quantum field theory, and most importantly for this talk, harvest entanglement from a quantum field. Before we look at entanglement harvesting, it's important to describe the quantum gravity model that we will be using and how quantum matter couples to this quantized gravitational field. So we quickly start with Einstein's equations, which describe our space-time metric in the presence of matter. And here we're using the square of the Planck length to simply denote the gravitational constant g. We'll focus on the theory of linearized gravity in the absence of matter so that we may assume T mu nu is 0. We'll consider small fluctuations of the background space-time by gamma mu nu, where gamma is small. And we'll be concerned with quantizing these linear perturbations, as this will describe a full field theory for gamma. And moreover, we'll assume that we're working in a background Minkowski spacetime, so that the final perturbed metric can be written as we see here. And the units in front of H simply give the quantum field H the same units as other quantum fields, such as the real scalar field and the electromagnetic field. We'll choose to work in the traceless transverse gauge, which will privilege an inertial observer with 4 velocity 1, 0. And the result of this gauge fixing is a wave equation for our linearized perturbations with 2 independent polarization degrees of freedom for each mode, which we can see in the resulting equation for H. And given this equation for H, it's also possible to define the Riemann curvature tensor in terms of the field H. And as we will see, the relevant components of a particle undergoing an inertial trajectory will couple to these components of the Riemann tensor in the weak field limit. So now that we have an equation for our field H mu nu, we discuss the quantization scheme that we'll use for the field. In order to quantize the field, we simply promote the coefficients of our wave equation to creation and annihilation operators, where these creation and annihilation operators satisfy the canonical commutation relations. And as a result of this quantization, we promote all gravitational observables to operator value distributions. Just as a quick example, our Riemann curvature tensor becomes a curvature operator. And now that we have a scheme for the quantized linear perturbations, now we need to understand how we're going to couple a localized quantum system to our quantized linear gravity. So we'll consider a localized non-relativistic quantum system, which we'll call the detector, undergoing an inertial trajectory with an associated free Hamiltonian and eigenstates n, so that the associated wave functions of the detector are given by psi n of x. And we need to understand the way in which this localized quantum system will couple to gravity. There's a number of different ways that we can arrive at an interaction Hamiltonian between our detector and the quantized linear perturbations. And our first approach would be to consider an effective Lagrangian for our detector. from which we can find the following interaction Hamiltonian. However, here we have an interaction Hamiltonian that's dependent directly on the gauge-dependent field H. There's a simpler way to prescribe the interaction Hamiltonian, which for our purposes yield the same results, but avoids the need to consider the gauge in the wave functions of the detector. And effectively, we obtained this quadrupole coupling here with the curvature, where the mass m is, where m is the mass of the detector, and x hat here is the position operator associated to the wave function psi of x. Using this Hamiltonian, we can expand in the detector's eigenbasis to arrive at the following interaction Hamiltonian. And we know right now that the product of the wave functions associated to different energy levels of the detector defines our smearing function. Moreover, we have that the coupling constant lambda is directly proportional to the mass of our detector, allowing us to more freely tune the strength of the interaction. We now make a few assumptions in order to reduce this interaction Hamiltonian into a form that is similar to the usual particle detector models. We restrict our detector to a two-level system, and we implement a switching function to control the time of the interaction. And as a result of these assumptions, our interaction Hamiltonian is given here, where omega is the energy gap given by the difference between the two energy levels associated to each wave function. And we note that in place of usual smearing functions, we now have quadrupole smearing tensors, which is expected due to the quadrupole coupling that we saw in the interaction Hamiltonian. Now all we're left with is coupling this detector to the quantized linear perturbations, and given the scheme from before and considering the interaction Hamiltonian, this simply amounts to adding a hat to the curvature tensor in order to make it a curvature operator. And our curvature operator is written as follows, given the results for the Riemann tensor in terms of the field H. Now, this interaction Hamiltonian here defines the particle detector model that we will use to probe linearized quantum gravity. So for our entanglement harvesting protocol, we'll have two detectors that are space-like separated, and we will assume that these detectors A and B will be inertially co-moving and identical. Most of the mathematical description from here is fairly similar to what Laura just described. We'll have two detectors, both in their ground state and the field in its vacuum state. The final interaction Hamiltonian will be given by the sum of individual interaction Hamiltonians for each detector. We'll apply a unitary time evolution operator to the density matrix and trace out the field degrees of freedom and obtain the density matrix seen here for the two detector system. Since each of our detectors was restricted to a two-level system, our density matrix can be represented by a 4x4 matrix, where LAA and LBB are excitation probabilities of detector A and B respectively, and all of the other terms in this matrix here are non-local correlations acquired between the detectors. And finally, since our detectors are identical, we also have that the excitation probabilities are the same. So given the density matrix here, we still need to define a way in which to quantify the entanglement acquired between the two detectors. So since we have restricted the detector to a two-level system, there are many ways we can choose to do so. Two of them being we can choose the concurrence, we could choose the negativity, and for our research, we chose to use the negativity. As a result of this, we find that the negativity can be written as we see here. So more specifically, the negativity is a competition between the non-local correlations between the detectors and the local noise produced by the vacuum. Now that we have a way to quantify the entanglement between the two detectors, we considered a number of different examples and studied the amount of entanglement that could be harvested in each case. And there are some important things to note that we need to prescribe. There are certain things we need to prescribe in order to study entanglement harvesting, these being the shape of the detector, the energy gap, the mass of the detector, which in this case is our coupling constant, the time duration of the interaction, and finally the separation between the detectors. So given two detectors,
4 minutes.
All right, perfect, thank you. So given these two detectors, that have strict values for these parameters, we can produce numeric results for the acquired entanglement. Briefly, we show a few different plots with different choices of parameters, and we do in fact see that it is possible to harvest entanglement from linearized quantum gravity. Now, with that being said, in order to truly understand how much entanglement can be harvested from the gravitational field, we must study a physical example. We'll choose to utilize hydrogen-like atoms as our physical detectors, since the wave functions of the atoms are able to fully capture the quadrupole coupling of the gravitational field. And atoms are also a convenient choice from an experimental standpoint, as they're easily accessible and controllable as detectors. And finally, when considering hydrogen-like atoms as detectors, it's important to note that the relative orientation between the two detectors plays a crucial role in the amount of entanglement that can be harvested. Effects of the relative orientation between each detector were seen from the dipole coupling between detectors in the electromagnetic field. And finally, this choice of atoms will allow us to draw comparisons between harvesting from the electromagnetic field and harvesting from gravity. So the following shows negativity between the detectors as a function of their energy gap. We see typical entanglement harvesting behavior where the negativity decreases as the separation between the detectors is increased. And next we show the negativity as a function of the relative angle between the detectors. We see that the relative angle has a large impact on the negativity, and for certain angles actually prevents entanglement harvesting altogether. With this in mind, it's important to note that despite being possible to harvest entanglement from the gravitational field, the negativity is 16 orders of magnitude lower than in the electromagnetic case.
This is 1 minute.
Okay, this is expected as the electron states are more sensitive to the electromagnetic field than they are to the gravitational field, which has important consequences in the entanglement harvesting protocol. However, we have reason to believe that for certain detector parameters, it should be possible to harvest more entanglement from the gravitational field than from the electromagnetic field. This is due to the fact that the coupling strength between a detector and linearized quantum gravity is determined by the mass of the detector. So we've shown how to extend the entanglement harvesting protocol to quantize linear perturbations, and that it's possible to extract entanglement. We've been looking at detector shapes and masses that allow us to harvest more entanglement from gravity than the electromagnetic case. This potentially allows us to measure entanglement harvesting from gravity before electromagnetism. And with some experimental verification, this could reveal quantum behaviors of gravity, as the presence of entanglement shows that the detectors must have been entangled with the gravitational field itself. This is everything I have for you guys today. Thanks so much for listening.
Thank you, Boris.
It went by a bit quickly. I couldn't quite understand what the detector was coupling to, whether it was a scalar field or gravity. I assume gravity, but I wasn't quite sure. But second, under the assumption it was, how do you see quadrupole effects when you have only two things? You need four things, don't you, to see it? I mean, you need this sort of up, down, back, forth kind of motion.
Sure.
You just
So,
say a bit more about that, please?
yeah, sure. So first off, yes, the detectors are coupled to gravity. We're coupling them to the linearized perturbations that we use. So that's specifically what they're coupling to. I guess I did go a little bit quickly over it. And you could see the quadrupole coupling when you have two wave functions of an atom. We have a choice of z-axis, but as the z-axis of one relative to the other kind of falls off, you'll start to see the effects of that quadrupole coupling depending on the angle between each of the z-axes in the wave functions themselves. That's kind of where we start to see the effects of it.
So one thing maybe I could say, Rob, these are not point-like atoms. They have atomic orbitals with angular momentum. Yeah.
So it's the finite size or shape of the orbital.
Mm-hmm.
So okay, that's good. So then in the limit they become point-like or tiny. Presumably those quadrupole effects get suppressed, I would gather. Did you look at that?
We specifically haven't looked at like in the paper we're working on now, we haven't specifically looked at the limit of the orbitals becoming point-like. I would imagine that you start to lose the effects of the quadrupole as the orbitals become smaller and smaller, just because, as you mentioned, you would need some kind of shape to the detectors to actually see that coupling.
Yeah, well, that's why I think it would be an interesting thing to see how it cares about both the size and the shape of the orbitals. Because something, I mean, eventually you can't see quadrupole radiation or quadrupole effects of gravity in some limit. I think that's an
Right.
important check. But okay, thank you.
Yep.
It's also interesting. You could have configurations of several of detectors trying to make antennas. There are interesting ways. It's a good suggestion. Yeah.